Good morning. Today we're going to talk about what happens when we have to factor. Everything that we talked about before, vertical asymptotes, points of discontinuity, are all the same, but obviously we can't find them when they're in this form, uh, or this form for that matter. I can do a couple things. I know that I'm going to have a y-intercept of 1 here, but in a non-factored form, rational functions are not as useful to us. So what we need to do to get any of these, the non-permissible values, vertical asymptotes, the x and y coordinates, the points of discontinuity, the x-intercepts, the y-intercepts, factoring this is going to be useful to us. So we've got this one here. We have two numbers that multiply to negative 12 and add to 11. I'm going to just do my explosion method. Two numbers are negative 1 and positive 12. Again, just basically doing our decomposition. Common factor of the first two terms is 3x. Common factor of the last term is negative 1. So this factors out to be 3x minus 1 and x plus 4. I do the same thing with the second, or the denominator in this case. Now in this case, I could still do the decomposition method because I know there's only two factors for 2. I know we have to start with a 2x and an x. And I'm going to play a little bit with my minus 4. I can have a minus 1 here and a positive 4 here. When I test that, I've got negative 2x plus 4x. That doesn't give me my negative 7. So my trial and error didn't work in that case, or hasn't worked yet. I'm just going to, if I flip that and I go negative 1 and positive 4 here, when I do my two middle terms, I have positive 8x and minus x. That doesn't work, but I can do trial and error to have our 2x plus 1 and our x minus 4. So our rational function ends up being 3x minus 1 over x plus 4 over 2x plus 1 and x minus 4. So now we can go ahead, our non-permissible values, x cannot equal to negative 1/2 and x cannot equal to 4, our denominators. We can't, now I'm going to see, before I do any vertical asymptotes, I'm going to see if I can cross something off. Nope, I can't. So I have vertical asymptotes that x is equal to 1/2 and x is equal to 4. So that's my non-permissible values and these. Points of discontinuity, because this is the reduced form there, since I didn't cross anything off, there are no points of discontinuity. The x-intercepts are going to occur where 3x minus 1 is equal to 0 and x plus 4 is equal to 0. So we have an x-intercept at negative 4 and an x-intercept at 1/3. Again, the x-intercepts occur in the numerator. And then finally, our y-intercepts, I'm going to plug in 0 everywhere. So y is equal to 3 times 0 minus 1, 0 plus 4 over 2 times 0 plus 1 over 0 minus 4. So what I end up on the top, I have negative 1 times 4. I have on the bottom, I have positive 1 times negative 4. This works out to be negative 4 over negative 4. So 1. Now, we have done everything we need to, or we can so far on that. We just had to do a bit of factor. Okay. Same thing with this one. What I see with this one in particular, I see a difference of squares for the top. So that's going to be 2x minus 3, 2x plus 3. And the bottom, two numbers that multiply to negative 24 and add to positive 8. Those two numbers are going to be positive 5 are going to be negative 8 and positive 8 and negative 3 will multiply to negative 24 and add to positive 5. Trial and error is possible, but since that 12's got more factors than I really want to work with, I will do decomposition. Okay. Blow up my middle term, take out an x, 2x minus 3, take out a 4. That's why. Take out a positive 4, that leaves me with 2x minus 3. So my denominator factors out to this. So our function is going to be y is equal to 2x minus 3, 2x plus 3, over 2x minus 3, and x plus 4. Now, before I go ahead and cross off stuff off, I'm going to say non-permissible values. X cannot equal to 3 halves. X cannot equal to negative 4. I am able to reduce this. Y is equal to x plus 3 over x plus 4. X cannot equal to 3 halves. So now we've got our reduced. We have a vertical asymptote at x is equal to negative 4. That's what's still left in the reduced form. I can't look for it. And then my point of discontinuity is going to occur where x is equal to 3 halves. So let's plug that into our reduced form. We have 3 plus 3 is 6 over 5.5. That reduces to 12 over 11. So my point of discontinuity with this one is going to be 3 halves, 12 over 11. Okay. So we know it was a point of discontinuity because it occurs where we get rid of this factor. Coordinates, the vertical x-intercepts, again, there's only one x-intercept. Sorry about terrible board work. The x-intercept is going to be where 2x plus 3 is equal to 0. X is equal to negative 3 over 2. So that's our x-intercept, and our y-intercept is going to occur where x is equal to 0. So y is equal to 2 times 0 plus 3 over 0 plus 4. So we have a y-intercept at 3/4. Now, we would be able to plot all those points on a graph and get a general sketch for this. Okay, so it's no different than what we were talking about yesterday, except I'm making you do some factoring. Guess I should have used that extra space, but oh well. Now, how do we deal with these guys? Again, we're going to have to factor before we can match. So this guy factors out just by taking in x with x plus 2, and then we have a difference of squares on the bottom. So that's our reduction. So here we have a vertical asymptote at x is equal to 2. We have an x-intercept at 0. So we need to find there's our vertical asymptote. There's my x-intercept at 0. And it's hard to see here. There's a point of discontinuity at -2. Okay? So this guy is your A of x. By looking for our important points, vertical asymptotes, x-intercepts, and points of discontinuity. This one here, I'll take out 2, that'll give me x plus 2, x squared plus 1. Can't factor x squared plus 1 because there's no number that's going to make that, there's no factoring because it's a sum of squares. Can't factor that. What that means is we would have a vertical asymptote where x squared plus 1 equals to 0. X squared is equal to -1. There's no solution to that guy. So for B, we have no vertical asymptote. And we have an x-intercept at -2. So no vertical asymptote and an x-intercept at -2. Here's our x-intercept, and I have no vertical asymptote. This one's this one's easier than what we did on the other board. Why does that keep happening? I don't know. We have two numbers that multiply to -6, add the +1, x plus 3 over x minus 2. And here we have x plus 2, x plus 1. So again, can I cross anything off? Nope. Make sure I've done that right. Yes, can't cross anything off. So I have vertical asymptotes at x is equal to -2, x is equal to -1. Excuse me. I have a x-intercept at x is equal to -3 and x is equal to +2. Now this guy's the only one that's got two asymptotes, and we do have our x-intercept at -3 and our x-intercept over here at 2. I hope it's easier for you to read on the other one. Well, no, that obviously means, so this guy here is c of x. That obviously means that guy is d of x, but let's just take a quick look at it. We factor this out to x plus 3, x minus 2. And on the bottom we have x minus 2, x plus 1. So what we have here is we have a vertical asymptote at x is equal to -1. We have a point of discontinuity at x is equal to 2. And then we also have an x-intercept at -3 over here. So again, a bit of factoring, and then the important points: vertical asymptotes, points of intersection, or points of discontinuity, and x-intercepts. I could also do y-intercepts, but those three things would be more than enough, as you saw in these graphs. need the space for factoring. Now, if I was to do this, we would have this, like I say, particularly nasty, i.e. I have a cubic function over a quartic function, or a cubic function over a quadratic function. Well, this guy's easy. We can factor this guy out to x plus 8, no, x plus 4, x plus 2. The top guy we got to factor out. Oh my, well, it's the cubic. We've known how to do this. We're looking for factors of 4 to test. Well, I'm going to use one of those two because maybe we'll be able to test those guys out. So let's see, p at 2, plug it in. I'm assuming most of you would use a calculator to do this, and that's fine. I'm just going to test. So I've got 16 plus 20 minus 22 plus 4. That does not equal to 0. Okay. Now test p at 4. Uh, 64, 128. 5 times 16 is 80. Minus 44 plus 4. Okay, that doesn't equal to 0 either. So I'm going to go back to my calculator. I'll test 1. So all I'm doing here is I'm punching in that expression, the cubic expression, and then I'm going to test -1. +1. Okay, +1 works. So p at +1 does equal to 0. So we get to do some synthetic division. 1, 2, 5, -11, 4. Bring that guy down. So right now we're factored out to x minus 1, 2x squared minus 7x minus 4. Two numbers that multiply to -8 and add to -7. I am going to quickly just do this in trial and error. I need a -4 over here and a +1. And I'm going to test to make sure that works out. Yes, it does. Now, what we have is our expression. Make sure that's going to work out. Okay. So, like I said, particular and nasty probably wouldn't show up very often, but we'll end up with this. And then we have non-permissibles at -4 and -2. We have vertical asymptotes because I'm not able to cross anything off here. Equations of our vertical asymptotes are x is equal to 4, or x is equal to -4, x is equal to -2. No points of discontinuity. Our x-intercepts are going to be x is equal to 1, x is equal to 1/2, x is equal to 4. Our y-intercept. Now the shortcut to do the y-intercept is just multiply the constants together because I'm going to put it 0 for x's. If So I got negative 1 times negative 1 times negative 4. So I have a negative 4 over a positive 8. My y-intercept is going to be negative 1/2. And the domain, everything except the 2 that are non-permissibles. So again, it's kind of ugly, it's nasty to do, but you have the skills when we go back to our polynomial unit. Now let's talk about horizontal asymptotes. Okay. So horizontal asymptotes, these are the lines. Vertical asymptotes are the lines that get closer and closer but does not touch vertically. Horizontal asymptotes are the same thing. As we extend the graph out to infinity, what happens? Well, there are 3 choices. It can approach 0, so our graph could start getting closer and closer to 0 but never touch. It can approach another number, like y is equal to 4, approaching net closer and closer but never touching. Or finally, it could go ahead and not have a horizontal asymptote. And it's fairly easy to work this through. Here we have basically what we have here is we've got a horizontal asymptote this one's got a horizontal asymptote with y is equal to 1. I know that's fairly hard to see. So basically, as we go out farther and farther, that's my horizontal asymptote. Here's my x-axis. That's why I was having problems with it. We have y is equal to 1. This guy down here, here's my x-axis. I have a horizontal asymptote at y is equal to 2. Here I have a horizontal asymptote along the x-axis, y is equal to 0. This guy again, this horizontal asymptote is y is equal to 1. This guy down here is going to be y is equal to 2. Again, here's my x-axis. This one doesn't have one. No horizontal asymptote. Down here, I can't read what that number is, but there's no horizontal asymptote at all, so I think that's a 3 here. Here we have a horizontal asymptote with y equal to 0, and down here we have one at y negative 2/3. Now, hard for me to read the graph, but I can pick them from this. So if we look at the guys that have y is equal to 0, okay, there's 2 of them. We have a linear function, x to the 0 over x squared. And up here we have a linear function over a quadratic function. I don't care about the 4. So if you think about this, as numbers get really, really, really big, this 4 really doesn't matter. So it really reduces down to 2x over x squared. And what happens here, in this case and the bottom case here, is as the numbers get bigger, that denominator, the squared part, overpowers the numerator. We have a lower degree polynomial on top than on the bottom. So if you've got a lower degree polynomial on the top than on the bottom, you're going to have a y or a horizontal asymptote along y is equal to 0. The other ones that have different numbers, we have y is equal to 1, y is equal to 2, y is equal to 2. Down here, y is equal to negative 2/3. What they all have in common is the degree of their, the degree of the polynomials are all the same. Now this case, it's 2 and 2. This one again, it's 2 and 2. So if you have a polynomial with this, a rational function where you have a polynomial of the same degree on top and as on the bottom, then you have a value, what is the leading coefficient divided by the leading coefficient. So here we have 1x squared over 1x squared. I don't care about the rest of that. That's just going to work out to be 1. This is 2x squared over x squared. That's going to reduce down to 2, and so forth. And finally, the third one is when you have a higher degree on the top than on the bottom. Here we have x squared over x. Here we have x cubed over x squared. We do not have a horizontal asymptote. And again, if you think about this in terms of putting really, really big numbers into it, 10,000 cubed over 10,000 squared is 10,000. 1 million cubed over 1 million squared is 1 million. So the three options that we have for horizontal asymptotes: a lower degree polynomial, on the top, and a higher degree on the bottom. If you have A over B, it is going to be the same degree, and we're looking at the leading coefficient over the leading coefficient. That's how you get that A over B. And then finally, the oblique or slant asymptote, or the one that we have no horizontal, we have the higher degree on the top and the lower degree polynomial on the bottom. So we can just deal with this in terms of the same base without technology. We want to know the horizontal asymptote. Well, we have in f of x, we have a second degree over third degree. So we don't have, if we think about this as we get bigger and bigger, basically we're going to have a number over a much bigger number. So what we have here is a horizontal asymptote at y is equal to 0. Second degree over third degree. Everything else I don't really care about. Find the highest degree. Here we have a third degree over a second degree. This has no horizontal asymptote. The top is going to overpower the bottom fairly quickly. Here we have a second degree over a second degree. Okay, we're going to have a horizontal asymptote at y is equal to 2 over 1. I'm looking at the coefficients in front of those highest degrees. Now, down here, it's a hidden. We have a third degree on top and a third degree on bottom. It's hidden, but it's there. So how do I find, we know we have a horizontal asymptote at some point. Now I'm just going to take the top. I'm going to have 1x times 1x times 2x. I'm going to have 2x cubed. So the leading coefficient is 2. And down here I have 3x times 1x squared. My leading coefficient would be 3. So, and again, here we have a second degree over a second degree. So we have a horizontal asymptote at some number y is other than 0. My top leading coefficient is 4 times 2, so 8. My bottom leading coefficient would be 3 times 1. It would be at 8 over 3. Okay, and that is the lesson for today. I will start going over some of these questions